Hello grade 12s. Today's lesson is all about the equilibrium constant. Now we have been talking about equilibrium, and we can define dynamic equilibrium as a point in a reaction where the rate of the forward reaction is equal to the rate of the reverse reaction. Another thing that's very important about dynamic equilibrium is that once a system has reached equilibrium, the concentration of the products as well as the concentration of the reactants remains constant. That does not mean that their concentrations are the same, but it means that the whole system settles on a balance between the forward reaction and the reverse reaction. Okay, so let's talk about this equilibrium constant. Now, the equilibrium constant in industry is very, very important because it is an indication of how effective an industrial process actually is. Now, this is important because it tells us how much money we're actually making. Okay, so this part is really linked to money. If a reaction is particularly effective, it means that we make a whole lot of money out of the process. Okay, and what industry is constantly trying to do is they're constantly trying to maximize the production of product so that they can get more out of the reaction itself. Now, when we talk about the equilibrium constant, we're talking about something that's abbreviated to Kc. So it's K with a subscript letter C. All right. This Kc value is really just a value. In other words, there are no units. Okay, so we don't describe units when we're talking about a Kc value because it is literally a ratio between the products and the reactants at equilibrium, and it's actually the concentration of the products and the reactants at equilibrium. It measures the success of production. In other words, it tells us how effective the reaction is. A very large Kc value means that there are a lot of products compared to the reactants, and this type of reaction is therefore economically sound or viable in industry. So what industrial processes want is they want as big a Kc value as is possible. Okay. It's only applicable at an equilibrium and at a specific temperature. So what we'll figure out a little bit later is that when we shift the temperature, we actually disrupt the entire reaction, which means that equilibrium has to be re-established. Okay, so it's very specific to a temperature. And the concentrations used are those present at equilibrium. So when we want to calculate Kc, we use the ones that are given to us at equilibrium. This one is important. This point is very, very important. It says that solids, as well as pure liquids, have an accepted concentration of 1. So remember, concentration is number of moles over volume. And when we talk about solids and liquids, in order to indicate a solid, we use an S in brackets. In order to indicate a liquid, we use L in brackets. Instead of using a concentration value, we use the number 1 in order to put this into the Kc value. And then let's have a look at what happens when we use the Kc value. Okay, so we're now going to learn how to write the Kc expression. Now, the Kc expression tells us how we're going to calculate Kc. It doesn't necessarily involve any values. And whenever you're doing this sort of problem, you have to start with the following equation. So you must start with Kc being equal to products over reactants. Very important. These square brackets are an indication of concentration. So whenever we put something into a square bracket, we're actually talking about a concentration. All right. So this is concentration of products over concentration of reactants. Remember, Kc has no unit because it is a ratio. So let's consider this as a hypothetical balanced equation that's at equilibrium. Okay. And when we write the Kc expression, we look at it in the following way. We've got our products over our reactants. We take the concentration of the one product raised to the power of the mole ratio in the balanced equation multiplied by the other product raised to the power of the number in the balanced equation over the same thing for the reactants. Okay, let's do an example very quickly. So here is a balanced equation that's reached equilibrium. In order to write the Kc expression, I'm going to say that Kc is equal to the concentration of the products over the concentration of the reactants. All right, and now I'm going to write the expression, the Kc expression. So I'm going to take the concentration of the products raised to the power of the number in the balanced equation. Can you see that? Over the concentration of the first substance raised to the power of what it is in the balanced equation. You can see, oh, I think I'm missing a number. Sorry, there should be a 2 in front here just to balance the equation. You can see that? Yeah. Yes, which means it's going to be raised to the power of 2, and then the second reactant is O2 raised to the power of what it is in the balanced reaction, which is nothing. Okay, and this is then the Kc expression for this particular reaction. Okay, and we always start off by writing that Kc expression. Just to recap, products, concentration of products over concentration of reactants, yes, in the square brackets raised to the power of the number in the balanced equation. Okay, we are now going to do a couple of exercises. Okay, so we're going to write down an expression for the equilibrium constant for each of the following reversible reactions. Let's look at the first one. We have 2H2O2 in solution, creating 2H2O, which is a liquid, plus O2, which is a gas. You should pause now if you'd like to try this reaction by yourself. Okay, just pause the video. So if I write the Kc expression, I'm going to say Kc, I'm going to start it off by saying products, concentration of the products over the concentration of the reactants, okay, because that's always how I start. And then I'm going to write the actual expression. So in terms of my products, I have O2, right, concentration of, multiplied by the concentration of my H2O. The problem is that it's a liquid, and so it does not get included in my Kc expression. That was one of the rules that we started off with. All right, so that means that there's nothing else. I could add the 1 in, but I don't need to. All right, and then I'm going to put that over the concentration of the reactants, which means it's the concentration of the H2O2 raised to the power of 2. And that is my Kc expression for that particular reaction. Let's look at the next reaction, guys. Again, if you'd like to try this by yourself, just have a look at it now. You can pause just as you are, and then you can try it by yourself. Okay, so let's get started. I'm not going to write this first bit because I'm out of a bit of space. I'm just going to write the expression for this time. Okay, so now I'm going to take the 3 products, and my 3 products mean that I have the concentration of the calcium chloride multiplied by the water, which is going to be 1, which means I'm not going to include it in the Kc expression. It's going to be 1 because it's a liquid. And I'm going to use the carbon dioxide, also raised to the power of the balanced equation number, which is 1. Okay, and then my reactants, I'm going to have HCl raised to the power of 2 because of the balanced equation. Are you with me? And then because the calcium carbonate is a solid, I also don't need to add it in to my Kc expression. So that then is our second example. Right, let's do a couple more. All right, so now I'm going to do the Kc expression for 1.3. Again, if you want to do it yourself, just pause the video. I have Kc, that's equal to concentration of my products, that's the NH3 raised to the power of 2 over the concentration of my reactants. That's N2 and then H2 raised to the power of 3. Good. That's my Kc expression. For the next one, let's have a look. Again, Kc is equal to concentration of the products. So I have HF raised to the power of 2 over hydrogen multiplied by my fluorine. Okay. And that's my Kc expression for 1.4. Let's do the last one for this page. Please note that it's very important that you check that your reaction is balanced first before you get started, so that you make sure that you write this down correctly. So Kc is going to be equal to concentration of my products. Yes, there's the second product over. Let's have a look at the reactants. SO2 and NO2 concentration. All right, good stuff. Right, so now we're looking at a slightly different type of question. And in this question, you've been given a value for Kc. Now, obviously, somebody has obviously written the Kc expression already, and they've substituted particular values in for the concentration. And now they're asking you to use your knowledge to get some information from this Kc value. Please note that the Kc value in this particular example is really big. The number 1 times 10 to the power of positive 13 is quite a big number. If you think of Kc being equal to products over reactants, in terms of our rules for a fraction, in order to get a big number like this, my numerator needs to be quite big. Yes, my numerator needs to be much bigger than my denominator in this particular instance. So what this tells me is that the concentration of the products is higher than the concentration of my reactants. Then the concentration of the reactants obviously at equilibrium. Okay, so what this tells me is that I'm going to get a lot of product out. Okay, so this tells me that this is a very economically viable reaction. This is a reaction that could make me quite a bit of money, because I'm going to get loads of loads of product out when I'm actually doing this particular reaction. Let's look at the next example. Okay. Please note that this value on the side here, okay, this Kc value, it's a big number, but it's not as big as the last example. So we also know that the concentration of the products is higher than that of the reactants, but this particular example, or this particular reaction, might not be making us that much money. Okay. Okay, this is my last example, and it's very interesting because, as you can see, the Kc value is tiny. 6 times 10 to the minus 28 is a really, really small number. And what it indicates to us is that when we create this fraction, it means that the denominator, in other words, the reactants, are much, much higher than the products. So here it tells me that the concentration of my products is lower at equilibrium, okay, than the reactants are, which means this particular reaction is going to need a little bit of help in order for us to actually make money from it. All right, for this example that I have, it's done slightly differently. We have a reaction that's reached equilibrium, and we want to calculate the equilibrium constant for the above reaction given the following concentrations. So not only are we going to actually write the expression, but we're actually going to do the calculation this time. So when I write down the expression, I'm going to say that Kc is going to be equal to the concentration of my products raised to the power of the number in the balanced equation over the concentration of my reactants multiplied by the concentration of the other reactant. Okay, I now have numbers that I can actually plug into this. So that's my product. HI is 0.16, and that's molar refers to a concentration, so it's 0.16 molar, which is my concentration, squared over the hydrogen. The concentration there is 0.02 molar, and then the concentration of my iodine is 0.02 molar as well. Okay, so that's then the answer. So we've taken the expression and we've plugged in the actual concentrations. Oh, I just need to change something. I beg your pardon. I'm sorry, but this is important. Once I'm writing down the concentrations, I can get rid of the square brackets. So just ignore that one for a second. What I should have written is 0.16 squared over 0.02 times by 0.02. All right, so do you understand that because I'm now dealing with concentrations, I no longer need to indicate that it's concentration by using a square bracket, so I just use normal round brackets. And then the numerical answer here is 64. So that means that the Kc value is equal to 64. That means that it's not a particularly big Kc value, right? So this particular reaction is not, it's not going to make us massive amounts of product. Okay. So those are all of the examples in terms of how to use equilibrium constants. Please make sure that you have a really good look at this. And I'm going to upload the PowerPoint, which gives you all of these examples. Please make sure that these examples are in your notes, grade 12s. Have a really good day.